Hey geometry students, Mrs. Fallon here. Let me fix my camera here for a bit. All right, so what we're going to do today is we are on page 285 and we are starting section 10.2. And so basically what we're doing is we've got a lot more vocab to go through. So I apologize for all the vocab in this unit, but you know what? Sometimes it's a necessary evil, right? So we got a lot of things we need to kind of talk about. And again, this is going to be a scenario which you're going to want to have a piece of paper because we're going to kind of do the vocab, but we're also then going to chat about kind of what it looks like. So that way you have a visual and not just kind of the words. Again, I love the fact that we can like know what the words are, the definitions are, but what I really need you to be able to do is to identify them and so forth. So, okay, we're going to start with something called a central angle. Kind of self-explanatory, I would think, maybe a little bit. So it's an angle whose vertex is in the center of a circle. So an angle whose vertex is the center of a circle. Okay, so grab a sheet of paper. Let's draw a circle. So we'll do a nice big circle. Okay. It's pretty good. All right, so let's do a center. So try to find the center point. So a central angle would look like this. So you would have kind of two endpoints on your circle, and then the angle, so it's like two radii that connect here. This angle right here, I'm going to call it theta, is called my central angle. And the reason why that one's a central angle again is because notice the vertex is the center of my circle. And so you can have, again, infinite number of central angles, but nonetheless, we have kind of that center of the angle there where the vertex is located. So for example, if I called this angle A, we'll do the center for C just because it makes more sense. So I would call this angle ACB. So I'm just going to kind of write on the side here just so it kind of matches our diagram. Angle ACB is a central angle. All right, so now we're going to get into a bunch of other stuff, which is different kinds of arcs. So a minor arc, and I'm just going to give you the definition first. It's the arc containing a central angle less than 180 degrees. So the arc containing a central angle less than 180 degrees. Okay, so what I mean by that is a minor arc is the measure of so the minor arc is this piece. Okay, I'm gonna use a different color here. So like, for example, it's this piece of the circle. So what an arc actually is the part of the circumference of a circle. So we have minor and major arcs. So like, for example, a minor arc has to have a degree that's less than 180. So for example, if I did, if I put another point over here, I could have another minor arc. You need 2 points to make up a minor arc. And so it's just a segment or a portion of the circumference of a circle. So it's that degrees, how much of a circle. If we know a whole circle is 360 degrees, what is this part right here? So maybe it's 45 or something like that, or 32, who knows. But that's what a minor arc is. And so a minor arc we always use, this is our symbol for arc, looks like an arc. And so on my diagram, I'm gonna call it AB. So a minor arc, just some notation so that you guys are aware, always contains 2 capital letters. So when you label it as arc, so we'll call this a minor arc. So when you label it as a minor arc, when it says arc AB, like that, it means you start at A and go to B. All right, so the order in which you write it makes a difference. Like if I were to say B and then A, technically, it could maybe mean this direction, right? So we're looking at kind of clockwise around our circle. And so the biggest part here is just to know that a minor arc less than 180 degrees is always going to be used, notation wise, is always going to be using 2 capital letters, and it has that little arc symbol above. So a major arc, as you maybe have guessed, is an arc that contains a central angle that's greater than 180 degrees. So kind of the same definition, just a little bit different. Okay. So what makes a major arc different, other than the fact that it is larger than 180 degrees, how you can tell is, number one, there still is that arc symbol, but you will have 3 capital letters. Whoops. So A, D, and B. So I'm going to add in another letter here. So let's go back to my diagram. So let's say I added in another point on my circle. Let's add it in down here. So again, a major arc then would, if I went from A to D to B. So the major arc, so arc A, D, B, you go in this specific order. So arc A to D to B. So what I'm referring to here is the measure from all the way around my circle. Okay, so it's basically from here all the way around. So as you can tell, that's going to be a much larger number, right? So if it's 360 degrees is how far, or what is the length, or the angle measure of the whole circle, right? So then a major arc is greater than 180. And again, we use 3 letters to denote it. And I'll show you some examples of how we're going to kind of use that. Okay, semicircle. So semicircle, as you guys probably already know, but a semicircle is 180 degrees. So it's exactly half a circle. So I don't know, however you want to kind of think of the definition. It's also half of the circumference. Remember, circumference is just like the perimeter of a circle, right? So a semicircle, let's do this. Okay, so I have my circle here. Let's call this X and Y. Well, first of all, do you know what we call what is this that I just labeled here, X and Y? This line segment is called what? If you said diameter, then you're correct. So what we're getting at here is that a semicircle includes the diameter of your circle. So the semicircle for this one, I don't know if I have another, a semicircle would be like here. That would be my semicircle. So that arc that makes up the semicircle is 180 degrees. A semicircle, in terms of like what an actual semicircle is, literally just means half of the circle. But if we're looking for the arc measure there, we're talking about 180 degrees because we're referring to the fact that it's half of the length all the way around. So you would also use, so even though it's not equal to 180 degrees, even though it's not greater than 180 degrees or less than 180 degrees, it's equal to 180 degrees. We are going to still use kind of 3 letters to represent it. So if I was going to use and mark off this arc, I would say maybe arc X, D, Y. And so I would say X, D, Y. So that's kind of how I'm measuring my, how I would measure my, my semicircle. That's how the notation would look. All right, so the rest of this is the measure of the minor arc. All right, so the measure of the minor arc is just the measure of its central angle. So it equals the measure of its central angle. So for example, let me go back to my drawing here. So let's say this measurement was 37 degrees, okay? Then arc AB is also 37 degrees. So how you would mark, how would you name this is you would say the measure of arc AB is equal to the measure of the central angle. So what I just did here is just said the measure of that arc, so that was my minor arc, is equal to my central angle. And so again, if we knew this was 37 degrees, then we know this is 37 degrees. Or whatever the case may be. The measure of the major arc, so think about this one, all right? So let's go back to our drawing here. If we know, by chance, if we know this is 37 degrees, okay? How do you think we figure out the major arc, the one that goes all the way else around? Well, yeah, I mean, you would just take 360 and subtract the 37. So to get the measure of the major arc, all you're going to do is take 360 degrees minus the measure of its central angle. So in our scenario, it would be 360 degrees minus 37. So our major arc would be 323, I think. Yep, so it'd be the measure of arc ADB. Notice I'm going to use measure, little m in front of it, is equal to 323 degrees. And so again, just some notation things I want you to pay attention to. All right, adjacent arcs. So adjacent arcs, kind of like the definition of adjacent, adjacent angles, that kind of thing. An adjacent arc, same deal, are arcs that are next to each other. So think about, they're connected. Okay, so they're next to each other, but importantly, I want you to add to it. I want you to say, and they intersect at exactly 1 point. So for example, let's go back to my drawing. So now that I have arc AB, and do you see I have arc BY? So arc AB and arc BY would be considered adjacent arcs. And the reason why is because there's two things. Number one, they're next to each other, but they also intersect, the arcs intersect in exactly 1 point. They both share common, that point B is in common. So that's what they mean by adjacent arcs. All right, next one, congruent circles. So congruent circles, congruent circles are circles with the same radius. So you might have already guessed, like all circles are similar, right? Because they're all just kind of like a scale factor of one another. But to be congruent, they have to be the exact same size, right? So in order for them to be the exact same size, they have to have the same radius measure. So they have to have the same distance from the center to the edge. I mean, you could also say they have the same diameter, right? But same deal. So they have to have that same measurement. And that's the defining characteristic of how you know that something, the circles are congruent. Next is congruent arcs. So they're arcs with the same measure. There's a couple things here. So arcs with the same measure. That's part of it. But they also have to have, they have to be arcs of the same circle or congruent circles. Come here. Shh. No one wants to hear you bark. Jack. Okay, let me finish writing this in and I'll kind of explain it. All right, so what I wrote here is, okay, so they're arcs with the same measure. That kind of makes sense, right? Congruent arc. We already know what congruent means. But they have to be arcs of the same circle or of congruent circles. So in other words, you can have an arc that's the same measure, but in two different circles. Okay, so what we're getting at here is either A, the circles have to be talking about the same exact circle, or you have to be talking about congruent circles. In other words, the circles have to have the same radius. One of those two things have to occur in order for you to have congruent arcs. So it's just kind of like an extra layer of, for this definition. And I'll show you kind of some examples as we go through some problems. And then last but not least, similar arcs are arcs with the same measure. All congruent arcs are similar, but not all similar arcs are congruent. So let me rephrase that because I think I said it wrong to begin with. They're arcs with the same. So similar arcs are arcs that are the same proportion. Okay, so for example, we know all circles are similar. Okay, so whether we have a small circle or a large circle, if the definition is still a circle, then they are considered similar circles. So for example, if this was a radius of 2 and this was a radius of 10, you know that it has like a scale factor of 5 to get from the small one to the big one. So with similar arcs, same deal. So if we know this arc measure here could be the same as this arc measure here, right? So they're proportionate in terms of how we kind of look at them. And so more importantly, what we're going to get at is this idea of similar triangles. Understand that they're like, they're scale factors of one another is kind of what I'm getting at. All right, let's kind of look through some examples. I think that might make some things look a little bit more, or hopefully be a little bit more clear. All right, so there's a whole bunch of different postulates and theorems in this section. And so again, a lot of this is going to get a little bit confusing because there's going to be a lot of them. So we're just going to kind of take it one at a time. So arc addition postulate. And again, I don't need you to memorize these. It's more about, some of this is more common sense, but I just kind of want to point it out. So it says the measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. Okay, so what they're getting at here is that I have arc AB, okay, and then I have arc BC. Those are adjacent arcs because they both share point B. Then I know that if I added, let's say this was, 40 degrees and this is 41 degrees, then I know that if I put the arcs together, then they would add up to the sum of those two, right? So obviously the arc from A to, well, that doesn't really make sense. Let's do 140 and 141. So what I'm getting at here is the sum of those two arcs are equal to the whole thing. But that's pretty common sense, right? You're just adding those two things together. Congruent circles, two circles are congruent. Two circles are congruent circles if and only if they have the same radius. So again, you need to either have them marked as congruent or you need to know that the lengths are equal. Congruent central angle theorems. In a same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding central angles are congruent. So notice that I have like this angle right here. Okay, that's a central angle because it passes through the center. If that angle is equal to this angle over here, let's say they're both, 40 degrees, okay? Then because the arc measure is the same as the angle, then that means the two arcs have to be equal as well. So if the two arcs are equal, the angles are equal. And if the two angles are equal, the arcs are equal. So they kind of go hand in hand. And so that's all really what this theorem is saying. Again, nothing too outstanding. It's just more talking about this idea of, kind of piecing together some of these definitions. And the last one on that page is literally what I said before, is that all circles are similar. They're all just kind of a scale factor of one another. Let's do some practice, okay? So let's jump ahead to page 287. Let's try some of this together so we can kind of just make sure that we're on the right path here. All right, so it says, identify the given arc as either a major arc, minor arc, or semicircle, and then find the measure. So let's first just go through and do major arc, minor arc, semicircle. So first and foremost, I can go through and label all my minor arcs. How do I know, without even looking at my diagram, remember, how do I know which ones are my minor arcs? So the reason I know that all of these are minor arcs is because of the way their notation, right? There's two letters. Anytime there's two letters, it's a minor arc. Now, with the three letters, it's either a major arc or a semicircle, because remember, we use three letters for both. So for the rest of them, like A to B to C, notice A, B, C. A to C is your diameter, okay? So anytime that the arc kind of contains, or that contains the diameter, then we know that this is a semicircle. Okay, A to B to D, that's more than a semicircle. This would be a major arc. B, A, C. So that goes from here all the way around. That's more than 180. So that would be a major arc. D, A, B. That's going to be more than 180. So that's a major arc. All right. So now that we've got the major and minor and semicircle stuff figured out, let's do the actual measures. So if we know this central angle is 40 degrees, I'm just going to kind of piece some stuff together here. Then we know this arc is 40 degrees. All right. So arc AB. Let's kind of go from here. So if we know that, okay, we know that okay, let's read this diagram here. A to C, AC is perpendicular to BE. So that means this is a right angle. So if this is 90 degrees, then what do we know about arc AB? Since this is a central angle, its corresponding arc will be the exact same as its central angle. So arc AB will have to equal 90 degrees. What do you know about B to C? Well, hopefully you know that that's also 90 degrees because this has to be a right angle as well. I didn't really ask you for that measurement, so we'll kind of just mark it on my diagram and kind of go from there. So A to B to C. So now ABC, it's a semicircle. We know what the arc of a measure of a semicircle has to be 180 degrees. All right, now to the next one, A to B to D. So I'm going to go 180 degrees plus 40 would give me 220 degrees. All right, B to C, that was that other one. Oh, I did ask you for that one. So that's 90 degrees. B, A, C. So if I'm going from B to A to C, I'm going all the way around. The only thing that I'm missing is 90 degrees in here. So I'm going to take 360 and I'm going to subtract 90. And what I get is 270. All right, D to A to B. C, A, B. So the only thing I really don't know is this arc A to D. So let's figure that out. If this is 90 and this is 90, that means, so this is a semicircle, this has to be a semicircle. So a semicircle is 180 degrees. If a semicircle is 180 degrees and this piece is 40, then this has to be 140. So now if I go from D to A to B, I'm doing 140 plus 90. So that's 230. All right, A to D. A to D we just figured out was 140. And then C to D we figured out to be 40. All right, so that's kind of what you're going to be doing in this section, is kind of using those definitions in those ways, kind of like knowing that, knowing what a central angle is, an arc, and all that kind of stuff. All right, in circle E, so that's the notation for what we mean when we say circle. So in circle E above, tell whether arc ABC is congruent to ADC. Explain why or why not. All right, so ABC and ADC. So they both make up a semicircle. So in circles, tell whether they're congruent. Yes, they are congruent. So yes, they are congruent. Why? You could say something like, I would say they are both semicircles. If you look at the diagram, that's kind of what it is. With AC as a diameter. So remember, a semicircle has to have that diameter in order for it to be a semicircle, right? So they both have the same diameter, AC. All right, in circle K, find the measure of DE. So DE is this measurement right here. So let's use our thinking skills to kind of work backwards. All right, so if we know this is 30 and this is 55, one of the things I always tell everyone to do is look for any diameters. So if you're kind of stuck on a problem, look for a diameter. If you know this is a diameter, then you know that one half is 180 degrees and the other half is 180 degrees. The other thing I would look for is vertical angles. So if this is 55 degrees, then this angle right here has to be 55 degrees. So now that I know this is a diameter, that means this whole piece right here has to be 180 degrees. So if I take 180 and I subtract off 55 and I subtract off 30, I would get, let's see here, 125 minus 30 is 95. I would get this to be 95 degrees. So all of this has to add up to 180 degrees. Okay. So now we know this is 180, 55, 30, and 95, plus 55. And the only part I really don't know is the part that I'm trying to find. So you could do 360 minus, you could do 360 minus all of this, or you could recognize that since this is a diameter, this is just 180 minus 55 and get 125. I guess we wouldn't really even have to figure those pieces out now, would we? But I'm sorry. All right, number 11, find the value of x, then find the measure of AB. All right, so this time I'm just kind of throwing in some expressions in here rather than just sticking with plain numbers. So here's what I want you to notice. This is a circle, right? How many degrees are in a circle? Well, 360. So what we know is that all of those things added up, so 5x plus 40 plus 70 plus 75 plus 2x has to equal 360 degrees. So let's go ahead and combine some like terms. So I have 7x plus 185 equals 360. Subtract 185, divide by 7. All right, so I've got x equal 25. Be careful, because it did say find the value of x, so yay, we did that. But then it says find the measure of arc AB. So the measure of arc A to B is 5x, which means it's 5 times 25, which we all know is 125 degrees. And that's how you would kind of end that one, right? So you would not only have to find x, but then plug it back in. All right, so that's all I really have for this. Again, I would practice this kind of on big ideas and just make sure you come to class with any questions. All right, bye for now.